Okay, this is a brief lecture on the wake, the hull efficiency slides we missed in class today. Start this, okay. So going back to our propulsion problem, we have this idea. We have our main engine here producing a certain amount of horsepower, and that's measured here as PS, the shaft horsepower. And then the shaft passes through a transmission, which might have a reversing gear and occasionally more than one forward gear down a long drive shaft out the back of the boat. So we can measure power here and measure power here, two different locations of the dynamometer, and the power on the PD. The delivered horsepower is going to be less than the shaft horsepower due to the losses in the transmission. The transmission efficiency can be given the non-dimensional number A to T. Typically that is, as I mentioned, about 95%. It's pretty high efficiency. Then we get to the propulsor. So between PD and what we care about is PE. That's the power needed to drive the bare hull at our ship speed VS against the bare hull resistance R. Between PD and PE are losses due to inefficiencies in the propulsor. And those are tied up here in this quasi-propulsive coefficient A to D, sometimes noted QPC, or quasi-propulsive coefficient. And those represent the losses, the efficiency, I guess, transferring power from PD, where the shaft exits the hull, to PE, basically where the rubber hits the road. So in between there are three coefficients. So this is the way it's done. It's separated into three pieces: A to naught, A to H, and A to R. We're going to focus on quantifying A to naught and A to H over the course of this lecture, and then primarily the next lecture where we plug in a lot of numbers. A to R is a rotational efficiency, and this represents losses due to invoking or creating circumferential motion in the flow. As mentioned in class, there are efforts to try to recover some of that kinetic energy, which is not useful kinetic energy, by using counter-rotating propellers in particular. We're going to assume that's 1 for, I think, all of our class exercises. A to naught comes from these open water tests. So in this simple scenario here, we have the propeller testing unit attached to a carriage. It's towing through still water in a tank. It's moving at some velocity VA through the tank, the advanced velocity of the carriage, and this propeller is working directly in uniform velocity. So it's being driven by a motor calculating measuring the thrust and torque. We talked about that in the prior lecture. These idealized uniform curves. As we discussed in class, these ships don't operate in, the propellers don't operate in a uniform environment. And so we're going to quantify the non-uniformity of that environment essentially using what's called the wake fraction, or Taylor wake fraction. Here we see a CFD study, has my lines from earlier today, a CFD study measuring different profiles along the hull, slices along the hull. And you can see the boundary layer along the hull, and here they're plotting essentially slices from about 0 relative to the free stream speed, so 0 speed, that's the no-slip condition on the hull, up to the speed of the hull. So this is a velocity field non-dimensionalized by the hull speed, or free stream speed. So at the hull it's exactly 0, and as we get out away from the hull, it gets back to free stream speed, which is going to be 1 here. And so you can see sort of that basically gives you an idea of the thickness of the boundary layer here. It's pretty thin. When you get in this part of the hull here, you can see how much it thickens up. And then that boundary layer, that slow-moving fluid, slower than V infinity or V ship, is what strikes the propeller plane here. This shows you an image of the propeller disc, and in this coordinates here, so this again, you're looking at V, the local velocity, divided by V ship, which in V ship you could think of it as V infinity, or the free stream flow condition. Out here you're close to 1, so this is essentially free stream flow, and then the slowest flow is occurring up here in the center portion where it's green, and that is directly right here. It's where the propeller is going directly behind the stem of the ship where it's attached. So that's very slow moving boundary layer flow that's impinging on the propeller blade. So as it's spinning around, it has a constant circumferential velocity, but the effective advance velocity hitting a section of the propeller is going to vary as it spins around. From slow advance velocity up top dead center here to a maximum advance velocity here and here. And that advance velocity affects the variations of advance velocity will induce variations in angle of attack of a given propeller section, such that the slower flow represents a higher angle of attack or higher loading on the propeller, and the faster flow represents a lower angle of attack on the propeller. You could also think of it in terms of our J, which is VA over ND, our advance ratio. ND is not changing, but the effective VA is the advance velocity, local advance velocity is changing. So our J is fluctuating between a low J, high thrust here, and a high J, low thrust here in terms of propeller performance. So as that blade goes around, it's experiencing, it's loading up and unloading once per revolution. Normally what this, so that was a CFD study. That's typically how things are plotted. We'll plot in a little, a slight variation of that, which is the wake fraction, which is its velocity defect, the difference between the free stream flow speed, or VS, and the local flow speed, VA, normalized by the free stream flow speed. So this wake fraction, if our local flow speed is the same as VS, our wake fraction is going to be 0. Essentially, there's no wake. It's at free stream conditions. If our local velocity is 0, meaning we are stuck right in the boundary layer, then a WT is going to be 1, and we have the largest possible wake fraction. So this diagram here essentially represents a very similar wake pattern from the previous CFD image, where we have a top dead center directly behind the keel of the ship, the largest wake fraction values, getting up to close to 1 right here. I see a 0.95. That's right in the slow moving flow where the velocity is very nearly 0. As you get out away from the bottom of the hull and outboard of the hull, moving in this direction here, it's the lowest wake fraction, 0.05. Essentially, this is free stream flow here. So you can see if you trace the path of just one section of the propeller as it swirls through the space, it's moving through very different wake fractions, which is the same as very different advance velocities. And it's got a higher loading up here and a lower loading down here. And so the circumferential variations are going to lead to loading variations around the rotation, which will drive vibrations. There's also radial variations. If we just take a slice here and we integrate along each circumference, we integrate the wake fraction, we can get a radial distribution, which near the boss is going to have a higher wake fraction or slower flow, slower advanced flow. As we move out away from the boss towards the propeller trip, we're closer to the free stream, and it will be a lower wake fraction. Now, the wake fraction varies over the propeller disc, but we need some kind of metric in order to represent the entire propeller disc, and that's what's known as the nominal mean wake fraction, which is essentially integrating this entire disk right here. So basically you integrate this value over this entire area right here, and you get some nominal fractions. So you have contributions of 0.6 here and 0.55 here and 0.45 here, and you add this all up and you have contributions close to 0 here, and the average is going to maybe end up being 0.2 or 0.3 based on just looking at it from here. These radial distributions, if you only had radial variations and no circumferential variations, you could deal with this by adding or subtracting twists to the profile. Now, since the boss section or near the hub of the propeller is actually loaded up more than it would be if everything was experiencing free stream flow, essentially if you had no wake, relative to the tip, this means you would actually twist down the sections near the hub to put them at a lower angle of attack than you would be if it was all free stream. So you can make some adjustment in the twist distribution if you knew the radial wake distribution. So that can be dealt with. The circumferential is more difficult. As you move through one cycle, 0 is top dead center when the propeller is right here. 180 is bottom dead center when the propeller is right here. So here we're going through a high wake fraction up here, the lowest wake fraction on the edges, and then a slight increase in the wake fraction as we get down here back behind the keel again. So as it moves around, the loading's varying along the entire propeller, and there's not much you can do about that. So you can try to reduce the vibration that's induced by changing the number of blades and then or adding skewness to the blades. You see how these blades are really swept back, impressively swept. And this allows a single blade to sort of be in a whole swath, circumference swath of the flow. So while the tip might be in a lower loading situation, the root is in the higher loading situation, so it sort of averages out. This is a pretty extreme example of skewness. We also talked about the afterbody effects, very slight variations in the geometry of the boat. It's easier to see through the section distributions, where you have right at the afterbody a fairly flat section like this, and then the propeller disc goes on like this. And here is an afterbody that has a very rounded, plump stern on which the propeller is attached here. And if we look at these circumferential distributions, ideally our wake fractions would just form closed circumferential loops. So we might have a radial distribution, but along a single circumference, like this blue one here, that section of the blade is experiencing a constant wake fraction, so it's not loading and unloading. So ideally you have circles, and the closest to that would be this propeller here. This propeller disc wake fraction distribution here. And this is the one that has sort of a rounded boat. So by rounding the boat, you can control the way the boundary layer impinges on the propeller to make it more of a circumferential. It's not quite circumferential, but it's better than the others in terms of loading. So the same propeller applied to these 4 different ships, or with 4 very similar ships with different afterbodies, you would have the least amount of vibration on this ship here. So you can actually control vibration, not by changing the propeller, but by changing the shape of the afterbody of the ship. How do we calculate wake fraction? We'll look at measurements in a second, but this is the wake fraction, one of the empirical formulas you may use. Essentially here they're linked it with block coefficient and length to beam ratio. As the block coefficient goes up, the stern of the ship, if this is the stern and this is the bow, the stern gets bluffer, meaning you have a larger wake, meaning you have a higher wake fraction. The flow is not recovering to free stream in that bluff body. So for a given length to beam ratio, as you go to a higher CB, your wake fraction is going to go up. For a given CB, if we cut across your length to beam ratio, see with increasing length to beam ratio that your wake fraction goes down. So essentially the ship is getting more and more slender as your length to beam ratio goes up, and it's more essentially hydrodynamic. So the wake is in a much thinner region, and you have a smaller wake fraction. It's measured typically with pitot tubes, so you can put a whole array. You can see this array of pitot tubes aimed at the flow to try to give you, here is a 3x4 array, to give you 12 points of information of what the wake distribution looks like. You can get a more spatially resolved method by using PIV. Essentially, PIV allows a laser to interrogate a plane of data. The plane is here. You seed particles in the flow, and as they flow past, you can interrogate in two quick successions, very close together. You take 2 images, and then you reconstruct the velocities in that plane by using PIV, or particle image velocimetry. Basically, software goes in, it looks at the 2 images, it lines up which particles are the same in both images, and just looks at the displacement between the images, divide by the time between images, and that gives you an idea of the velocity, magnitude, and direction. It's a pretty powerful technique, and it's a non-intrusive, whereas the pitot tubes can they're interfering with the flow field. This giant structure array is modifying the flow field. The wake, as long as your particles are at a fairly low density and they're buoyant, neutrally buoyant, this is a non-intrusive method. The laser light doesn't affect the flow field. So let me go back. Let me just see one thing. I just wanted to mention one thing, and I apologize for skipping that. I get dizzy here. So the key thing here, this is the definition of the wake fraction. So you see the relationship. Once we can determine a nominal WT, or a WT for a give that represents a given propeller plane, this allows us to compute the advance velocity that's needed for the propeller calculations. The propeller calculations, you need to know what's the relative velocity, the relative free stream velocity for the propeller, the velocity flowing into the propeller that we use for our advance ratio. This is the ship speed. So they are different. The advance ratio, the advance velocity is going to be smaller than the ship velocity. And how much smaller depends on this wake fraction. If the wake fraction is 0.5, that means it's half the ship velocity. And typically it's going to be a little bit smaller than that. It'll be about, wake fraction maybe 0.3, which means the advance speed is going to be about 70% of the ship velocity. So the flow felt by the nominal flow experienced into the propeller is less than ship speed, around 70%. The other key term that we're going to use to get at the efficiency and ultimately allow us to calculate the horsepower needed on the boat is the thrust deduction. And so we'll just sort of gloss over this because it's quite a complex thing, but I just want to hit some of the key points. Essentially, by putting the propeller on, it modifies locally the flow field in the stern. As we mentioned, we first talked about propellers. If you have a propeller disc here for momentum theory, it pulls the flow in, right? So you have these converging streamlines. The flow is moving this way. The action of this propeller is to cause a pressure jump and momentum jump across it. It's adding momentum to the flow. That's the job of the propeller. That's what the horsepower does. And so compared to the free stream velocity out here, it's already accelerating as it hits the propeller disc and then accelerating even more on the backside across the disc. So the propeller itself modifies the flow in the stern of the ship, and it causes these sort of array of things to happen just by putting it onto the boat. So up to now we've calculated resistance of bare hull boats without a propeller because it's complicated to include the propeller. The effects of the propeller essentially affects that resistance, and that we can quantify through the thrust deduction. So we have, what does it do? A key thing is this. The propeller accelerates the velocity near the stern, essentially sucking water over the stern faster than it would normally be flowing on the stern in the absence of the propeller. That actually leads to reduced flow separation, and by keeping the boundary layer from separating, which is a favorable effect, but ultimately it's an unfavorable situation. You have an increase in ship resistance, and that's largely because you've enhanced the viscous stresses. You've essentially artificially enhanced the viscous stresses over what they would be without the propeller by having the propeller running and pulling water at a faster speed than it would be without its presence, which leads to enhanced stresses. So ultimately, you need more thrust than the bare hull resistance. So in the simplest sense, we think, okay, we calculate the resistance of the ship, and how much thrust does the propeller need? Newton's second law in the x direction tells us R must equal T. But the fact is, by having T, capital T, or thrust, means we have a propeller, and that propeller has modified the flow field away from the flow field we used to calculate this R. And we have to keep that into account. That's done through this thrust deduction factor. T, which is the difference between the thrust and R, divided by T. And T is going to be, ultimately the thrust you need is greater than the bare hull resistance because of the effects of the propeller. And you can write it this way as well, that the thrust is going to be equal to that bare hull resistance over 1 minus T. Now T is pretty tough to get at. It's definitely tougher than wake fraction to get at. There's a couple different approximations. There's one here of linking the thrust deduction to the wake fraction that we just talked about, with that coefficient linking that Kr being in this range, 0.5 to 0.7. So T might be around somewhere around 0.2, and that indicates here that our thrust is equal to the bare hull resistance divided by 0.8, whatever that works out to, about 1.2. So thrust would be about 1.2 that of the bare hull resistance. So this takes that into account. You can still go ahead and do bare hull calculations, but now we need to take into account that the thrust needed by that propeller, when we go to do our propeller calculations, we need the propeller to produce an amount of thrust that is greater than the bare hull resistance, because the action of the propeller itself adds to the resistance of the boat. That's T. So you have the two things where hull efficiency has an effect are T and WT, the wake fraction and the thrust deduction factor. So we come back to our quasi-propulsive coefficient. Eta naught we're going to get from open water tests. We'll be doing that on Thursday. You'll be doing that in your homework. And we'll be doing that also in the lecture a week from this Thursday as well. We'll be doing that again. Then you have this rotation efficiency, skip to that, which we're going to call 1. And finally, the hull efficiency, which is 1 minus T over 1 minus WT. So that shows you that having a non-zero thrust deduction factor leads to a decrease in the efficiency. However, having a non-zero Taylor wake fraction leads to an increase in the hull efficiency. And you may, when you calculate 8H, you may find that it's greater than 1. This is the way that it's written. It's a strange kind of thing that you might have an efficiency greater than 1. But rather than, because we're including these effects in this manner, that's enabled. It's fine. So you might find that this is the case, not always. So we need to know a T and a WT. So T and WT affect A to H, which affects our powering computation. So again, once you've computed your effective power, that's the horsepower to push the bare hull ship at the speed Vs, then if you know A to D, that allows you to calculate PD, because PD is just, in your typical efficiency calculations, PD is equal to PE over A to D. So if you know both the right-hand side, you can get to the delivered power. And if you know the transmission efficiency, then you have PS is going to be PD over A to T, which is pretty close to 1. So that allows you to get from this, basically from your effective horsepower to your shaft horsepower, which is the horsepower you need, your actual engine horsepower. So it passes through all these efficiency factors as you go along. And we're looking to compute all of those. The transmission efficiency, we're just going to assume some numbers. So some simple example, we'll just work, we won't get all the way through this, but we're looking at some simple numbers. Here's a boat with a given block coefficient, length, beam, effective horsepower, that's been calculating with your bare hull calculations, where you're computing the resistance R and multiplying by the ship speed, and that's your effective horsepower. You've done that in a couple of problems now. And there's your ship speed in meters per second. So use a single screw formula from the book. That's a function of block coefficient and length to beam ratio, all of which information you have. You get a Taylor wake fraction of about 0.4, 0.375. Use a simple formula for thrust deduction, also listed in your chapter in the wake fraction, and 0.1875, which is essentially half of that value. That's linked, that simple formula links T and WT, as we showed here. To assume 0.5 for KR, so T equals 0.5 WT. It gives you this value for T. Then we have a hull efficiency. As I mentioned, it can be greater than 1. It's a strange, kind of a strange beast. Then, so that will enable us, once we have our, if we have our effective horsepower, which we do, we make some assumptions about the transmission, will get us to our shaft horsepower once we have A to naught. And that's where our focus is going to be on Thursday, is getting to this. To get to the open water propeller efficiency, we're going to be looking at these typical propulsion curves where you have an efficiency that moves like this. Here's J and KT, and you have thrust curve and your 10 times KT curve, 10 times KQ curve here. So we'll need to know KT and J in order to get at the efficiency eta naught. How do we get at the KT? Well, KT is non-dimensional thrust. What is the thrust of the boat? The thrust is related to the resistance of the boat, but it's not equal to the resistance of the boat due to this, the effects of the propeller modifying the resistance, as we discussed when we talked about thrust deduction. So that's the link between thrust and resistance. You need this thrust deduction factor to get at that. And you have, and we need to calculate J, which requires the advance speed. The advance speed is linked to, again, we have VA equals VS times 1 minus WT. So we need the ship speed, we need Taylor wake fraction, and we can calculate the advance velocity. So there's two places that they come in. One, T and W come in. One is computing the hull efficiency. The second is to compute VA, which is needed for the advance ratio. And the third is to compute the thrust needed by the propeller, which is needed to compute the propeller open water efficiency via the thrust coefficient. And so we will go through a calculation, a complete calculation Thursday. So there are some devices to control the wake. I showed these in class earlier. Essentially, the flow. In this case here, what happens, actually it's shown better in this diagram, is the flow, because the shape of the ship is actually like this. It's sort of fatter in the middle and skinnier, and the keel is here, so the flow kind of follows that shape. So it's impinging on the propeller at an angle to the propeller. And so the idea behind this situation here is to try to do two things. These are sort of upside down wings. You can see that they're cambered like this if you look closely. By cambering like that, it tends to push the flow. If the flow is moving this way without them, let me pick a bit different color here. About green, lime green. If the flow is moving this way without them, it tends to pull them down, so they're more normal, more parallel with the flow and impinging on the propeller, parallel to the axis of the propeller. This thing up here is a converging duct, and it takes the flow and accelerates it through here to try to create higher speeds up here than there would be without that duct in place. And so remember, these Taylor wake diagrams tend to have the slowest speed right up here for a single screw ship, because that's right behind the keel of the boat. And so these things are trying, there's one on the other side too, this is the keel of the boat. There's one on the other side, they're trying to accelerate the flow through here to reduce the wake fraction here, to make it more similar to what it is down here at bottom dead center. So that's the story.